Good afternoon. My talk derived out of a project that started off last year, and I've been doing a lot of work over at Fort Stanton and in Snowy River, and the issue always comes, well, what's the elevation of this relative to the elevation of that when those two things are 1,000 feet apart? Because you want to know which direction is the water flowing. Is the water flowing from the main passage to Snowy River, or is the water coming from Snowy River and flowing to the main passage, or do neither meet and they're both flowing somewhere else? And so you have the issues. So a trip was put together back in May of last year to go ahead and see if we could actually figure this out. The person who put it together hadn't really spent a lot of time thinking about the logistics of doing the survey, and started off with some 3/16 thin wall tubing. And before we spent more than 10 minutes playing around with it, we discovered that that just wasn't going to work. And luckily, we were still in the field house, and it was still on Saturday afternoon, and places in town were still open. So once we made the determination that that system wasn't going to work at all, we went into town, bought a bunch of half-inch tubing, and we bought them out of all the braided tubing. So we got 80 feet of that, and then we got another 20 feet of unbraided thinner wall. And then we got some joiners, and then we got some valves, because I figured, well, you know, you got a lot of water in there, you better be able to shut it off, because otherwise how are you going to transport this into the cave and back out, and then from station to station without losing a lot of water? Okay, so suffice it to say, that's what we cobbled together in the next 4 hours. We found the sticks. The sticks are these maybe 1/4 inch by 2 inch stakes that you use for doing surveys. We found a couple of those, and I happen to have a bunch of Velcro, so we Velcroed everything together, cobbled it together, and it demonstrated in the field house that, yes, you could hold these things up, and the water was actually level between them. You know, someone had done a theodolite survey around the interior of the building and put up these nice markers, crosshairs, so we could go to that. You know, not only that, we could just hold them next to each other and see if they lined up. So that's what we took into the cave. It was fun. When you have 100 feet of tubing and you don't necessarily have a lot of distance, well, when can that happen? Well, do you have a slope? Well, the passageway between sewer pipe landing and Snowy River has lots of slopes in it. So you're limited in how far the two stadia rods can be apart by the amount of slope. The top of one stadia rod needs to be higher than the bottom of the next stadia rod. You know, otherwise you can't make your measurement. Also, if that you don't keep that in mind, water comes gushing out one end of your instrument, and you waste a lot of water, which happened on multiple occasions. So this shows setting up, we're at sewer pipe, doing some stuff, and then, you know, this is going up, there's a passage that goes up from what is relatively flat and level just past sewer pipe, called Roaring Hill, and this is actually at a slope of about 30 degrees. So it took several shots just to get up this slope. And then just past Wayne there's a ladder which goes almost straight up, and it took a few shots to get up that. And you notice we got lots of tubing. So one of the points when you're doing these kind of trips, you try and learn from all of the grand mistakes that you make and from all the hardships you encounter. One of the things we realized that, well, 100 feet is probably not the optimum length of tubing. You know, something smaller, maybe closer to 50 feet is better. We also learned that using the thin wall plastic tubing is a kind of a bad idea because it's squishy, and if you're surveying in tight passageway, you might be laying on the tubing. Well, that ends up generating all kinds of errors, especially if the tubing is squishy because the levels keep going up and down. The braided tubing is much better about that. Even various little twitches will cause all kinds of problems. The valves, okay, there's all kinds of human factors issues with the valves. Trying to get everybody to open the valve, close the valve, and oh, by the way, only one person should open their valve at a time, because if you both open it at the same time and you're wrong about the elevation, water comes spitting out at high velocity. Especially half-inch tubing, you can get rid of a lot of water really quick. So that doesn't work. So we learned all kinds of wonderful things going through this survey. So when I got back, decided that, well, let's put down what we learned, and let's see if we can find a better way to put together a survey system based on a water level. Now, we, of course, were not the first people to use water level in a cave. A guy by the name of Art Palmer from back east is noted to have done that, like, I don't know how many decades ago, and they actually named it after him. They called it a Palmer pool. So he has since stopped using water and has moved off to a auto level system. But if you're trying to do this in a somewhat inexpensive fashion, well, a water level is relatively inexpensive compared to things like an auto level. So wrote down all the specifications, tried to do all the calculations, tried to figure out, okay, so half-inch is excessive. What's the smallest size? And I've actually built prototypes with 1/4 inch and 5/8, and that works out actually really good. 3/8, not 5/8. So started iterating through. So this was the first version of it. And then, Bob and I were doing some survey with it, and Bob commented afterwards, says, like, those valves really suck. First of all, there's a big flat spot on that valve, which holds it away from what you're trying to measure, which introduces parallax problems and other stuff. So we thought about it for a while, and I designed some screws for it. I'd also thought that, well, having a 45 at the bottom would be a good thing because, well, if you're trying to get close to the ground, you don't have to worry about bending. But as it turns out, and Bob pointed this out also, is that, well, you can just do a straight out the bottom, and the difference in how close you can get it to the ground is actually pretty small between having a 45 there and not having a 45 there, because the tubing's pretty flexible, so it's not something you really have to worry about. So, and Bob also pointed out one other thing, is that, well, if you have a particular thing in mind, I've got this handy-dandy printing device, and we can actually print you out the parts in plastic. He's got a 3D printer. It's really cool, and that's one of the parts sitting there. And here are some of the other parts that have been printed out. Something to hold the tape, sliders to help you read the tape properly, and then what's showing there is this bottom part which holds the bottom of the tape. So the 3D stuff worked out really nice. Learned a whole lot about 3D printing. It's not without its problems also, but when you're trying to prototype stuff, it's great. All right, so what you do is you prototype a bunch of parts, and you take them out and you try them out. And Bob's got this course set up around his house. It's got 6 stations, and so we go survey it, and 6 stations is really all you need to show all the shortcomings of anything you design. All right, so this is the next iteration. We decided, the regular valves, get rid of them. So what will we replace it with? Well, we got another valve that twists. Okay, so the twisting valve does several things. When it's closed, it keeps all the mud out. So everything's capped. When it's open, it can breathe so they can level just fine. And at the same time, if you drop it or someone is way off on the levels, it limits how much water you can lose, which is actually of great benefit, because human factors, it turns out, is one of the main causes of errors with these systems. You know, human factors is where we've spent a lot of time. And you'll notice that we've now gone to, you know, straight out tubing. This happens to be, you know, 1/4-inch ID tube. I think what we're going to stay long term is the 3/8 is the minimum tube, minimum diameter that we're going to have. We've got rigid sight tubes, and what that does is it gives you a really nice area to read. You don't have to worry about, you know, is the water in clear tube, or is the water in there, which is a little bit difficult to see. You can see it, but it's kind of difficult. And you can't dye the water. Why? Well, if you got regular dirt and mud, who cares if you dye the water? You know, if you spill it, it's going to blend in. Well, you know, Snowy River is pristine white. You get red dye on pristine white formation, BLM is just not so happy. So, unfortunately, we can't use colored water. Okay, so another problem that we had was, you know, like getting the stadia rod the right length. So what we've got here is a collapsible tripod that's got quick release, so you can extend it to as long as you need and get it just the right size. All right, so, and then, of course, we've got an ever plenty supply of tape here, so we can make this as long as you want. And the current version, we've got extendo tubes, so if you need to extend it out to 8, 9 feet, you can do that. And, well, when would you need 8 or 9 feet? Well, if you're going up something basically vertical, having 8 or 9 feet between stations is very convenient. All right. So this is the design, this is the model for that screw cap. So what you do is you design it and 3D print it, okay? So you've got all the holes exactly where you want them, you got the threads where you want them, you got the O-ring lands where you want them. But, you know, 3D printing has certain issues, one of which it's not entirely precise. So what you have to do is you have to run the threads, such as they come out of the printer, through a die and chase the threads and make them the correct dimensions, okay? So you have certain things like that. Now, at the other end, you take PVC parts that you can buy in the store and glue them together, drill it, and then tap it for the mating end of this. Okay, so this is what the system fully extended looks like as it exists today. And we've been out testing it, and again, we've gotten rid of, you know, like 80% of the human factors issues. We're still working on a couple that are nagging, but we tend to have an error of 2 millimeters per station, and that's loop closure error. So we're doing pretty decent. So that's 2 millimeter closure error per station. Not too bad. Okay, so this is what the part that holds the tape is. Now you notice this one's got Velcro on. Well, that one's got screws. Well, that's so that you can bolt this down and clamp it so that you don't have issues like this. You know, like this is a little bit wobbly. So, again, being able to 3D print these things relatively inexpensively, it's easy to go through iterations and make improvements to your design so that you don't have things, you know, like all cattywampus and screwed up. So now it takes 2 bolts to hold it down. It takes, you know, 4 bolts to bolt it to the piece. And we would have had them, but, you know, there was an issue with the printer. But, you know, such is life. You know, it just takes it a few days longer to get things done. This is the slider, which is, we actually have 2 different designs. We have one with an innie, and we also have one that's got an outie. And there's pluses and minuses to either one. And Bob and I are still debating over whether an innie or an outie is better for reading the scale. It's a question of who makes the most errors with which one. Bob makes fewer errors with one, and I make fewer errors with the other. So we need to iterate on that design concept a little bit more before we've come up to something that we actually like. All right, so this is what the entire system cobbled together looks like. The entire system, as you see it there, weighs approximately 10 pounds. It's like 9 point something or other. If you go with the 3/8 tubing, it goes up by approximately 4 pounds. So again, the benefits of going with the bigger diameter tubing is that if you do, while you're transporting it, manage to get air bubbles in the tubing, it's way easier to get the air bubbles back out of the tubing. And when you transport, even with the valves closed, you'll get air in the lines. And there's ways to do that while you're going into the cave, like you fill them completely full of water so there's no air. But better to have a system that's easily maintained inside the cave and isn't going to cause you a problem. All right, I think that's it. So we're still iterating on the design. The fact that we are now consistently able to do loop closures at 2 millimeters per, the system is actually basically usable as is. But there are several improvements that we need to make to improve the human factors issues and stuff like that. Any questions?
And what are you going to use this for and over what distance?
Okay, good question. Okay, the design of this is to go from DD1 at the sewer tube landing, which these names might not mean anything to you, out to the north end of Snowy River, which is where the sump is. Okay, that's roughly 1,500, 1,700 feet of passageway. Okay, so now there's several reasons for wanting to do that. One is you want to know what the relative distance is between where Turtle Junction meets Snowy River to know if the water can go up, down, or somewhere else. You also want to know what the elevation of that point is above Government Spring, which is the known resurgence, okay, which is another 1,500 feet more or less as the crow flies. So we've got a precision survey to DD1 at sewer pipe landing. So now we've got another 1,500 feet. And Bob has done the calculation and said, well, as long as you are within 1 foot, then you basically have the data that you need. The design of this was to ensure that you could easily stay within that 1 foot. My target is, no more than like 20 millimeters. But well, it backs up at Crystal Creek, which is at the terminal sump, and it backs up currently 16 odd feet. Okay, plus or minus, depending upon where you want to measure from, and there's issues with where they put the data logger. So that will tell you how much head you've got to run how much water through this alluvial pipe or alluvial filled pipe. We don't know exactly what the pipe work is between the 2 points. It's believed to be a conduit of some kind, but nobody really knows. Water seeks its own level.
Yes, okay.
And you got a stadia rod here.
There's no change in level.
That's
Explain.
right. Okay. So it's actually fairly simple. So you've got a stadia rod at point A. Okay, and you hold up your water level to the point. Now you got another stadia rod over here. This one's lower. So you extend it out, and you have your water level, and you read what this number is from that point, and you read what this number is from this point, and that tells you what the difference in elevation is.
From the floor, I got it.
Right. Well, from the points that you're measuring on.
Right. So it tells you the precise change in elevation.
Yes.
So what's the maximum change from station to station you can do with this?
With the extendo tubes, it'll go 9 feet.
Okay, so you can see a 9-foot change.
Yeah. Yeah. So if you need to go up something relatively vertical or sloped, you know, you've got 9 feet. Yeah.
Are your errors normal, or is there asymmetric? Are you more likely to have an error when you're
Given the data we have today, all of our errors are in the same direction, so that indicates a systemic error of some kind. But is it an instrument systemic error, or is it a human factors systemic error? I can't answer that question today. More testing and more design work will be necessary to be able to answer that particular question. We want to get to the point where the error is random. We're not there yet. You know, currently, you know, I see a consistent loop closure with, you know, between, you know, if I close every single station, I see a 2 millimeter loop closure error in the same direction every single time. So that tells me that there's something in there causing the error, but is it the instrument or is it us? I don't know. Yes.
I know that it's not me.
Well, we try and read the bottom of the meniscus, you know, and you know, your standard basic chemistry stuff. You know, where do you read on the scale? And we're trying to read the bottom of the meniscus, but that doesn't explain consistently where the error might be.
You know what might help is a level on the pillows.
The design has a level on it. The level hasn't been implemented just yet, but you know, the design calls for having a level on the pole, and you know that, you know, if you have like a, you know, a 5-degree error, you know, that can give you you know, 1 to 2 millimeters per meter of elevation difference. Okay, so that is certainly one of the considerations. And so when we finish iterating through the design, then we'll put the level on. You know, right now I don't want to glue a level on and then, you know, have to scrap it with the rest of the device because I glued it on. You're looking at, you know, like 20 millimeters over the course of you know, like 75 readings.
That's almost 7,500 feet.
Well, call it 50 foot per reading. Okay, so you know, you can do a kilometer, so that's, you know, like 2 centimeters per kilometer elevation error, which is, you know, like right where you want to be.
Sounds insignificant.
Exactly, and that's Bob's continuing point is, you know, you only have to be this good.
Yeah, you don't have to be much better than that.
Right. Well, and that's Bob's continuing point. Okay, any other questions? All right, thank you.